All right. Hello, good morning, everybody. I hope you're having a good week. I want to spend a quick minute just talking about the upcoming stuff that we're going to be doing because we have sort of a goofy split over spring break. So today we're going to be doing more derivative formulas, which are exponential and logarithmic. And then on Thursday, we're going to do the first half of the chain rule lecture. So the chain rule is sort of one of the more complicated rules that we cover. And so we do it over 2 lectures. So we're going to do the first half on Thursday. And so since we're only doing half of it, that means that there's no mini quiz for the chain rule on Sunday. So the mini quiz will happen after we've covered the second half of the lecture. However, I do sort of recommend that you start the homework that won't be due till after spring break, but not to put it off because it is kind of long and a bit, algebraic and intensive because the chain rule is a little more complicated. So my recommendation is that you try some of the homework from the stuff we do on Thursday before spring break, and then you finish it after spring break. But there is no mini quiz on Sunday, just the mini quiz on Wednesday for the stuff we do today, and then the homework due on Sunday for the stuff we do today. So if you're looking at Moodle and you sort of see that it looks a little goofy, that's why. So I just wanted to give you a heads up about that. So as I mentioned, today we're going to sort of be continuing with our derivative formulas. And today we're going to be talking about exponentials and logarithmic functions. So I'm going to go ahead and switch over to the DocCam. Give me 1 second here. And so we're still just sort of building our formulas based on, patterns that mathematicians have seen that give us formulas. And so when we look at exponential functions, I just sort of want to give you a visual so that the formula makes sense. Let's think about the function 3 to the x, right? If we were thinking about what was going to happen at 0, right, we would want to pick values near 0 to approximate the derivative. And we would do, f of 0.1 minus f of 0, 0.1 minus 0. We would approximate using, right, the equation for the secant line. We do it to the left and to the right, and we would get some value for the instantaneous rate of change at 0. Okay, now if we were to do this for all points, for 0, for 1, for 2, for all the points in between, and we were to graph the derivative, so the original function is this black line, exponential going up, the derivative is almost the same exact function, right? It looks very, very similar. It's only off by a tiny little bit, right? Which is kind of weird. So then if you were to do the same thing, right, with 2 to the x, right, turns out that the function and the derivative are also very, very similar, right? So we start thinking, okay, well, they are so close in shape that we're expecting the derivative to also be exponential, right? These are exponentially shaped graphs. And you can tell that they only vary by a little bit. So it seems as though they are exponential with some constant that is the difference between the original function and the derivative. So it turns out if you were to do this for 4 to the x, 5 to the x, 6 to the x, right? So a whole lot of these exponential functions, there's a pattern. And when we get patterns, that's how we get formulas, okay? So here we have the function a to the x. So that's a general function with a base a. So a could be 2, 3, 4, whatever it may be. It turns out that the derivative is the same thing back. So a to the x, it's an exponential function, times the natural log of the base. So it is multiplied by a constant, but the constant is related to what the function is, okay? So, for example, you have 5 to the x, right? The derivative is going to be 5 to the x times the natural log of the base, which is 5. So this natural log of 5 is a constant, and 5 to the x is a function. And that function is the same as the one we started with. Now, there's a couple of spin-offs from this particular formula that are going to be special cases that we are going to be using. Okay, so this is the general formula. You can always use the general formula and default to it, but let's see what sort of happens with our special cases. So let's consider e to the x. So this is an exponential function, but now our base is e. E is an irrational number. It's like 2.71. It shows up a lot in nature, things like that. We know that it has a special relationship with the natural log. If we apply our general formula, that says we get the same thing back, e to the x, times the natural log of the base, okay? The natural log of e is 1, and anything times 1 is just itself, right? E to the x times 1 is just e to the x. So that means that the derivative of e to the x is just e to the x. And that's because when you apply the general formula, that constant is just a 1. Okay, so that's our first sort of special case. And now our second special case is sort of a special case of the special case. So if we have the function e to the cx, where c is any number, so e to the 5x, e to the 10x, e to the 12x, right? If there's a constant up in the power, we can do a little algebra. So I'm going to do this over the side here. E to the cx algebraically is the same thing as e to the c to the x. So we can separate the power by raising one power to the other power, because if you raise a power to a power, you multiply those together. So you can also separate them, which means if we want to take the derivative of this, this is the base and x is the power. So the rule says, the general rule is that you get the same thing back, so e to the cx, times the natural log of the base. So the base is actually e to the c. It's the whole entire number. So times the natural log of e to the c. Well, similar to the last general case, if you have the natural log of e to the c, that is just c, right? The c will come in front, and the natural log of e is 1, which means that the derivative of e to the cx is e to the cx times c, okay? So this is how we sort of deal with exponential functions when an extra number shows up in the power. We do have to do some of the algebra in the background to figure out how to apply the derivative. But for ease, it is a special case. Okay, so even though we have 3 rules here, there's really only one rule, right? The derivative of a to the x is a to the x times the natural log of a. You can always apply this and still get these derivatives. These are just special cases that if you happen to remember, it'll save you a little bit of time. Okay, so last time we had these 3 derivatives. We had a constant, we had mx, and we have x to some power. Today we're adding on a couple different things, but the first things we're adding are exponential rules. Okay, we're going to add another rule later. We also had sine and cosine, which are not here. We're not going to look at those today again. So when we add on these rules, I want to remind you that I will often refer to these rules as the basic derivatives. And when I say that they are basic, that does not mean they are easy. Okay, so it's really easy to associate those 2 words together. When I say they are basic, I mean they are foundational, as in we are going to use these to build upon for other derivatives we look at. So if I say you have to use the basic derivatives, that doesn't mean easy. So if I'm saying basic and you're like, hey, this is complicated, and now I feel like I should know this faster, that's not what I mean by the word basic. So just keep that in mind as we sort of work through chapter 3. Basic means foundational. Okay, so we're going to start by just practicing our a to the x rule and our e to the x rule. So there's 4 derivatives here I want you to try out. We have 7 to the x, e to the x, 1.2 to the x, and pi to the x. So I want you to take a quick 2 minutes, see if you can sketch out the derivatives of each of these using this rule so you can start to get comfortable with them, and then we will go through them together. Okay, take about 30 more seconds. All right, so let's look at each of these and make sure we can apply the formula. So for the first one here, we start with 7 to the x. So we have to identify the base. The base here is the 7. So we get the same thing back times the natural log of the base. And so again, I really want to emphasize that in the derivative function, 7 to the x is the function part, and natural log of 7 is a constant. It's going to be really important for us to remember what is a function and what is a constant as things start to get more complicated. And I will highlight why that's going to be important in a few minutes. You'll sort of see where this might cause some confusion. Okay, so for the next one, we have e to the x. So that is one of our special cases. The derivative of e to the x is e to the x. And so we don't have to add the natural log of e to it. We could, but since the natural log of e is 1, we end up with just e to the x. For part C, we have 1.2 to the x. So again, we're thinking about what is our base here, right? And so our base is 1.2. So we have 1.2 to the x times the natural log of 1.2. So here, again, we're thinking about how this all works together. This part is a constant, the natural log of 1.2, and then 1.2 to the x is our function. And then finally, last but not least, we have pi to the x. Pi is a little bit goofy. We don't usually see that as a function, but there's no reason why that can't be the base of a function. So we just see that it's an exponential function, that the x is in the power, and we think, okay, exponential rule, and we just follow the map here. So we get pi to the x times the natural log of the base, which is pi. Okay, this one's a little goofy, but it's meant to remind you that you can do this with any type of exponential function. And so you just sort of trust the process of, the derivative function here. So now we're going to add on another derivative, which is the companion of the exponential functions, which is the natural log of x. So here, it turns out if you do the same process where you're evaluating at each point of the natural log, that when you sketch it out, the derivative ends up being 1 over x, okay? And this is where what I was talking about before comes in. The derivative of the natural log of x is 1 over x. However, if you have something like the natural log of 7, right, and you were asked to take the derivative of just this by itself, the derivative is 0 because this is a constant. There's no x in there. So that's why I was saying you need to be careful about recognizing what is a function and what is a constant. So the only time this formula applies is when the variable is in the function. If it's the natural log of a number, the derivative would be 0. Okay, so just keep an eye out for that. So here, we now add that to our list. The natural log of x has a derivative of 1 over x, okay? So now what we want to do is we want to think about the other sort of rules we were talking about, like the constant multiple rule, the sum and difference rule, the second derivatives, all those sorts of things we talked about last time. So just as a reminder, the constant multiple rule says that if you have a constant in front of the function, then when you take the derivative, it's that constant times the derivative of the function. If sums and differences, if things are added or subtracted, you can take the derivative of each one separately. And then the second derivative is when you apply the same process to the first derivative to get to the second derivative. So we're going to practice some of these. The first one I want you to try uses the constant multiple rule and the sums and differences rule. So we're really trying to think about how do things like this 2 or this 3 or addition and subtraction, how do we put that together with what we just learned about the derivatives? So I'd like you to try this out. I'm going to give you 2 minutes, see if you can work out these derivatives, and then we'll go through them together. Okay, take about 30 more seconds. Okay, So for each of these, we're going to go term by term to get the entire function for the derivative. So here, our first term that we're working with is 5 to the x. One of the key things that we have to get really good at is just recognizing that it is an exponential function. So today we are mainly working with exponentials, and last class we were working with polynomial terms, but in the future, it won't be so isolated. So looking at a term and saying, yep, that's exponential, or yep, I should use a power rule, because these are two different rules, so we have to make sure we know what kind of function we're working with. So the derivative of 5 to the x is 5 to the x times the natural log of 5, which is the base. And then our second term, we have minus ln x, so that's the natural log rule. We said the derivative of the natural log is 1 over x. And then finally, we have the constant multiple rule. So we have 2 times, and then the derivative of 3 to the x is 3 to the x natural log of 3. So our derivative shakes out like that. And one thing that I really sort of want to highlight is this part right here. So the 2 is part of the constant multiple rule, but algebraically, you cannot combine the 2 and the 3 to the x. So this cannot become 6 to the x. There's nothing we can do to combine these because the 2 is a constant and the 3 to the x is a function. Okay, so we are not going to combine these two in any way. 2 is a constant and the natural log of 3 is a constant. So theoretically, we could, if we wanted to round, we could turn this into a decimal and multiply the 2 and the natural log of 3 together. Typically, we're not going to do that, but nothing can be combined with the 3 to the x because that is the function part. Okay, so be careful about that. For the second one, again, we're going to go term by term because they're separated by addition and subtraction. The first term is e to the x. So we said the derivative of e to the x is e to the x. And then the second term, again, constant multiple rule. So here the 3 is going to multiply the derivative of the natural log of x. So the derivative of that is 1 over x. And I do want to point out that sometimes we write the second term a little bit differently. So you may also see this as e to the x minus 3 over x, right? So 3 times 1 over x is the same thing as 3 over x. Both of them mean the same exact thing. One is not more right than the other. So, if you're doing homework, whichever you prefer is fine, but I want to make sure you know the same thing. So if you're doing like a mini quiz and you see this, but you wrote this, you know that it means the same thing, okay? So for part C, we're going to take the derivative here. Again, term by term. So we start with 10 to the x. The derivative of 10 to the x is 10 to the x times the natural log of the base. So the base is 10 here. So we have 10 to the x times the natural log of 10. Plus the second term is 5 times the natural log of x. So again, the 5 is a constant multiple. So 5 times 1 over x, or you can write it as 5 over x. And then finally, the last one here, the first term is e to the x. So the derivative of e to the x is e to the x. Plus the derivative of 6 to the x is 6 to the x times the natural log of 6 minus, now the derivative of ln x is 1 over x. So again, when you have constants in front, they multiply the derivative. And if you have things separated by addition and subtraction, you just go term by term and find the derivative of each piece. Okay, so the next thing we're going to practice is second derivatives. So again, last time we talked about second derivatives and how they work. So I want to talk just briefly about what we're going to do here. So the function, we have 2 to the x plus e to the x minus x to the 2/3. So this is not exponential. Keep that in mind. You'll have to think back to last class. Minus ln x plus 6. So we want to start by finding the first derivative. So we're simply going to employ the addition subtraction rule, go term by term and try to find the derivative of each piece. Then I want you to try to come up with an exact answer. So notice the word exact for f prime of 1. So you're going to plug in a 1 everywhere you see an x in the first derivative, And then you're going to look at each term and determine what can and cannot be simplified to still be exact. Okay, which means you shouldn't be turning anything into a decimal that is not, how do I want to say that? That's not terminal, right? So you don't, like if you have e to the 1, you want to leave it as e to the 1. You can't really turn that into a decimal and still have it be exact. Then you're going to find the second derivative. So you're going to go to the first derivative and again, term by term, apply the rules to get the second derivative. Once you do that, you're again going to evaluate the second derivative at 1 to make sure that you can sort of look at the different terms and figure out what can and cannot be simplified in certain ways, right? We want an exact answer. So I want you to try this out. I'm going to give you 3 minutes. The second derivative is a little bit trickier than the first derivative, but try your best, and then we will go through this together. Okay, take about 30 more seconds. All right. So when we start off by finding the first derivative, again, we're going to go term by term since they're separated by addition and subtraction. The first term, we have 2 to the x. So that's an exponential function. We see the variable up in the power. So the derivative is 2 to the x times the natural log of 2, since 2 was the base of that function. The derivative of e to the x, we're going to get the same thing back, e to the x, minus, now here, as I mentioned, this is a power rule. So you see that x is in the base. And so we have to invoke the power rule here since there's a number up in the power. So the number will come down in front and we're going to subtract 1 from the power. So that's what we were working on last time. So hopefully you were able to remember or reflect back on what we did last class to get that rule in. The natural log, the derivative is 1 over x. And then the derivative of 6 is going to be 0 because 6 is a constant. Okay. So here we have the first derivative of our function. And now what we want to do is we want to plug in a 1. So we're going to do this in 2 steps. First, we're going to literally plug in a 1 everywhere we see an x, and then we're going to talk about what can and cannot be simplified. So here we're going to have 2 to the 1 times the natural log of 2 plus e to the 1 minus 2/3 1 to the negative 1/3 minus 1 over 1. Okay. So we've just put in a 1 everywhere we see an x, and now we're going to look at each of these terms to figure out if it can or cannot be simplified. So the first term, we have 2 natural log of 2. We don't usually write the 1, but the natural log of 2 is an irrational number, so we are not going to turn that into a decimal. So since we want an exact answer, that first term, we're going to leave as 2 natural log of 2. We're not going to write the 1 because anything to the 1 power is just itself. Similarly, the second term is e to the 1, right? Same thing. So you don't want to turn e into a decimal because it's an irrational decimal. It goes on and on forever. So we're going to leave this as e. We don't need to write the 1, so we can write plus e. Just for reference, if you do want to leave the 1 power in there, that's fine. It means the same thing. Okay. Now here is where we can do some combining. So the last term, we have 1 over 1. 1 over 1 is just 1. Right? Now, this other term looks really complicated, but what we need to remember is that 1 to any power is just 1. So 1 to the negative 1/3 is 1. So this is negative 2/3 minus 1 is the calculation that we're going to be doing here. So negative 2/3 minus 1. So the negative 2/3 is from here, and the 1 is from the 1 over 1. So when we compute that, we get the common denominator, so minus 2/3 minus 3/3, and we get minus 5/3. So we can simplify this into minus 5/3. But again, we're going to leave it as a fraction because thirds are not a decimal that, is terminal. So we're going to leave it as minus 5/3. So this is how we would write the exact answer without losing any of the accuracy. Okay. So now let's go ahead and talk about the second derivative. Okay, so here we want to go back to the first derivative, which is f prime of x, and we want to look at each piece. So here's where we need to be a little bit careful. So look at this first term. We have 2 to the x times the natural log of 2. So as a reminder, the natural log of 2 is a constant, right? And if we have a constant times a function, we need to use the constant multiple rule, which means that when we find the second derivative, that this natural log of 2 is going to multiply the derivative of 2 to the x. So this is the same constant as this. We bring it down from the constant multiple rule, and now that multiplies the derivative of 2 to the x. The derivative of 2 to the x is 2 to the x times the natural log of the base. So what ends up happening is that we end up with 2 of these natural log of 2 terms. And so that can be a little confusing. So I want to make sure we understand why there's 2 of them. One of them comes from this constant multiple rule, and the other one comes from taking the derivative of this 2 to the x function. So now we have 2 of them. Okay. The next term is e to the x. The derivative of e to the x, still just e to the x, good old e to the x, right? The next one, now we're back to our polynomial term, right? So we're going to be using the power rule. And what I notice is that a negative 1/3 is going to come down and multiply this minus, and those are going to cancel, and I'm going to end up with a plus. So negative 1/3 times minus 2/3 is going to give me plus 2/9 x, and now I have to subtract 1 from the power, so that gives me minus 4/3. Okay, again, be really careful subtracting 1 from the power. Okay, and now this last term is really, really interesting. Okay, so remember, this last term came from the natural log of x, but now it is turned into a polynomial term. So we do have to rewrite this. So as a reminder, 1 over x is the same thing algebraically as x to the negative 1. So now we have to use a different rule to get to the second derivative. So this is the same thing as x to the negative 1. So when we take the derivative, the negative 1 comes down in front and cancels the minus. And then when we subtract 1 from the power, we get negative 2. Okay, so again, we started with the natural log. We used the natural log derivative to get 1 over x, but then we had to use the power rule derivative to get to the second derivative, which is x to the negative 2. So that's a little goofy. So now, again, we want to see what's happening at 1. So our first step is just to actually plug in a 1 everywhere, just like before. So 2 to the 1, natural log of 2, plus e to the 1, plus 2/9, 1 to the negative 4/3, plus 1 to the negative 2. Now we're going to go term by term to think about how we can simplify this, and if we should simplify it. So the same thing here, we're not going to turn natural logs into decimals because that's going to lose accuracy, but I will do a little algebraic simplification since there's 2 of them, the natural log of 2 times the natural log of 2. I'm going to write this as 2, which is the 2 that's in the middle, times the natural log of 2 squared, right? Because there's 2 of them, like 3 times 3 is 3 squared. Natural log of 2 times natural log of 2 is natural log of 2 squared. Then plus e to the 1, we said was e. And now again, we have some constants at the end. 1 to any power is 1, which means we have 2/9 plus 1, right? Because 1 to any power is 1. So 2/9 plus 1 is the sort of calculation we need to work out. Remember, 1 is the same thing as 9/9. So when we add these together, we get 11/9. So combining these, we get plus 11/9. Okay, so the algebra is really interesting on these, and I hope that by thinking about how to present these as exact numbers, it helps you remember some of the ways we think about algebraic terms. Okay, so first derivative, second derivative, plugging things in, talking about exact answers. Now, the next thing we want to do, as you may have guessed would come up at some point today, is to find the equation of the tangent line. So we did this a bunch last time, and so there's a process. And we can apply that process again here. And what's different is that now our function is exponential. So as a quick review of what we need to do, in order to find the equation of a line, we need a slope and a point. Okay, the point we can get by plugging the 0 into the original function. That'll give us the y value. That's the point that the tangent line touches the equation. That's the shared point. To get the slope, we need to use the derivative. As a reminder, the derivative is the slope of the tangent line, right? So here, we're going to find the derivative, plug in the point we're interested in, then we'll have a slope, we'll have a point, and we'll put that together with y equals mx plus b. Okay, so I'm going to give you 2 minutes, see if you can work that out. If you have notes from last class, there's also sort of a map on the equation of the tangent line if that's helpful, but then we'll go through it together. Okay, take about 30 more seconds. All right. So again, we need a point and a slope. It doesn't matter which one you do first. Okay, so I'm going to do the point first. So here, if I plug a 0 into my function, I get 2 times e to the 0. Anything to the 0 power is going to be 1. So then 2 times 1 is 2, which means when x equals 0, y equals 2. And so the point that is shared between the tangent line and the function is 0, 2. So that's where the tangent line touches. Now I also need the slope. And so I start by finding the general derivative. So the derivative of 2 times e to the x. 2 is a constant multiple. The derivative of e to the x is e to the x. Once I have my general derivative, I'm going to go ahead and plug in the x value that I'm interested in finding the rate of change. So I plug in my 0. So I have 2 times e to the 0. E to the 0 is 1. 2 times 1 is 2. So that means I have a slope of 2 here. So now I have a point and I have a slope. So I'm going to bring in my y equals mx plus b, where I'm going to plug in the slope. So y equals 2x plus b. Now, when x is 0, y should equal 2. So I have 2 equals 2 times 0 plus b. 2 times 0 is 0. So that tells me that b also equals 2. There's a lot of 2's in this particular problem. That's just a coincidence. So here, putting everything together, we have y equals 2x plus 2. So remember, your ultimate goal is a linear function. We're finding the equation of the tangent line. So you shouldn't have anything like x squareds or e to the x's in your final answer, because we're looking for the linear function to represent the tangent line. Okay, so we're going to try one more of these, but now with a natural log function. Same process. We need to find the point. We need to find the slope. We need to put it all together. So take 2 minutes and see if you can work that one out, and then we will go through it together. Okay, take about 30 more seconds. Okay, so again, we need a point, we need a slope. I'm going to start with the point. So again, we're interested in what's happening at 1. So I'm going to plug a 1 into the original function. So the natural log, that 1 is crooked. So the natural log of 1 is one of the special values of natural log that actually has an integer value. So you may know it, or you can plug it into your calculator to double check, but the natural log of 1 is 0. Okay, if it wasn't, like if we were looking at x equals 2 or x equals 4, we would leave it as the natural log of that number, right, to be exact. But the natural log of 1 is 0, and 0 times 3 is 0. So when x equals 1, y equals 0. So we have the point 1, 0. We also need the slope. So we're going to take the first derivative of our function. We see a constant multiple of 3 here. So we have 3 times, and now we're going to take the derivative of the natural log of x, which we know is going to be 1 over x. So now we want to evaluate what that is at 1. So we have 3 times 1 over 1, which is 1 times 3, gives us a slope of 3. Okay, so now we have a point, we have a slope. Now we're going to use that to find the equation of our line. So we start by plugging in our slope, y equals 3x plus b. Now we take our point, we have when x is 1, y is 0. So here we have 0 equals 3 plus b. We subtract 3 from both sides, and we get b equals -3. Okay, so putting that all together, we get a final equation of y equals 3x, that's our slope, minus 3, that's our b value. So again, we get a linear equation, which represents the equation of the tangent line. And again, this is a very common application that we use for different derivatives. And as we learn different derivatives, we can substitute those in for f of x. What's important is that we are always applying the same process, even as our derivatives get harder and harder. Okay, so now we're going to do an example that sort of brings in a lot of things that are important in business, but also requires that we learn some new terminology and some new variables to think about how this may all apply. So when we start off, this is a long problem. We're going to go piece by piece. But when we start off, we're aiming to understand the variables before we bring in any derivatives. Okay, so here's the situation. When money is invested, it gains value depending on a lot of different things, right? So the market and the global economy and where you invest it and, all those things, risk. One of the factors is how the money is compounded. So what does that mean? So if you are in an investment account, then you are guaranteed some sort of money in things like savings accounts or bonds or certain vehicles that you can put money in. And compounding is how often the interest is added to your principal amount, so the amount that you have in the account. And so this may not be something you've ever thought about. So if the interest is added once per year, so one time per year, the bank or whoever goes in and says, okay, you have X amount of dollars, I'm going to multiply that by the interest rate and drop the interest into your account. Okay, that's called compounding annually. So once per year, they look at your balance and they give you interest based on how much is there. The equation that we use for annual compounding is given by FV equals PV 1 plus R to the T. Now, this equation uses variables based on how we see this in the textbook for 127 and 128. You may have seen this equation with something different than FV and PV, but it's the same equation in, say, an economics class or a business class. So if it looks familiar, but you use something different than FV and PV, it's the same equation. This just happens to be the variables they use in our book and that are used in 128 as well. So that's what we're going to be using. So FV over here, this is the future value of your money. So how much money you're going to have at the end of your investment. PV is called the present value. So that's the amount you initially invest, how much you're putting in today into this account. R is going to be your interest rate. So when you put money into a savings account or you buy I bonds or something that you know you're going to get money from, you are told typically the interest rate on that day that you invest, right? So right now it's abysmal. So you can get like less than 1% on a savings account, but right, R is the interest rate. And when we use this particular formula, we use it in decimal form, right? So we know how to go back and forth with percentages to decimal form, but when you're doing calculations, you have to write things in decimal form. And then time is T, and time is always given in years, right? We're talking about annual compounding. So how many years are you leaving your money in that account? So we want to get comfortable just with these variables and with this equation. So for part A, we have, suppose that you invest $1,000 in an account that has an interest rate of 2.5%. I want to know how much money is going to be in that account in 5 years. So the point of this problem is just getting comfortable with where you plug in the different numbers here. So I'd like you to take a minute and a half, right? If you have a calculator or even a cell phone calculator, see if you can just plug these in and compute this using this equation with these numbers. Okay, so try it out and we'll go over it in a minute or two. Okay, take about 30 more seconds. All right, so the $1,000 is the present value. That's the amount that you're going to put in today. Future value is what we're trying to find, how much you have in 5 years, so in the future. So then we have 1 plus R. So R here is 2.5%. So we need to convert that into a decimal. So 0.025. And then up here we have time. So time here, time T is 5. So we need to make sure that this number is raised to the 5th power, but this number is not. Okay, so when you crunch that in your calculator, hopefully we get the same value here, $1,131.41. Okay, so at the end of the 5-year investment, that's how much money you will have, which is more than you started with, based on this interest rate. Okay, so now this is how we start talking about compounding. So another way to compound money is to compound it monthly. And if you have like a bank checking or savings account that you get interest, it is likely that it's compounded monthly. This is the common way that they do it. So that means that once a month, you get interest added to your account, okay? But it's really, really important that you understand that you do not get the annual interest rate each month. So you don't get 2.5% every single month, right? Instead, they take that 2.5% interest rate, divide it by 12, and you get 1/12 of that interest rate every month, okay? So if you had an investment in a 12% vehicle, you would get 1% each month for an annual interest rate of 12%, but a monthly interest rate of 1%. Hopefully that makes sense. So we have to adjust our equation for when we're compounding monthly. So the way that we do that is we still have our initial amount, our present value. We have our 1, but now we divide our interest rate by 12, right? Because you're only going to get 1/12 of it each time you get interest. But that means that you're getting interest 12 times every single year, right? Not just once per year. So up here in the power, we have 12 times t, because you get it 12 times per year times the number of years. So that's how we would adjust this equation for monthly. If we were going to do it daily, we would have r over 365 raised to the 365 times t, right? If you were going to do it quarterly, so once every quarter, you'd have r over 4 times 4t up in the power. But we're going to talk about monthly here. So what we want to do is we want to say, is there a difference in compounding monthly to compounding annually? Will it be the same amount? Will we get $1,131.41? Will we get less money by doing it monthly, since we're dividing by 12 and getting a little bit each time? Will we get more money? So we want to run the same problem. So $1,000, 2.5% interest, 5 years, but we want to see what happens when we compound monthly. So I want you to use this equation and run the numbers again to see, is it the same, is it bigger, or is it smaller? Before you run the numbers, I want you to make a guess. You can just make it in your head, or you can write it down. Do you think it'll be bigger, smaller, or the same? And then go ahead and run that number into this equation. Try that out, and we'll go through it together in about 1.5 to 2 minutes. Okay, take about 30 more seconds. Okay, so let's make sure we know how to set up this equation with the same numbers as before. So present value is the same. So that's 1,000. 1 plus, now we have r over 12. So 0.025 divided by 12. And then up here in the power, we have 12 times t. So 12 times 5. So you have to be a little bit careful when you're entering this in your calculator. It's really, really easy to make a mistake with parentheses or things like that. So just be careful. I make mistakes on that all the time. So just be extra careful. So here, when we crunch these numbers, we get $1,133. Okay, so you'll notice that when we did it compounding monthly, we actually got slightly more money than when we compounded annually. And you may think, hey, like that's not much of a difference for an extra like $2, like, you know, $1.50. But I want you to imagine if you're investing $10,000 or $100,000, right? Or your retirement account at some point gets to $1 million. All of a sudden that difference is really pretty important, right? And so thinking about this, if you go to make an investment and you have a choice between 2 banks, and one of them compounds annually and gives you 2%, and one of them compounds monthly and gives you 2%, now you know that monthly is going to get you a little bit more money, right? Why does that happen? Because every month when that interest is drawn and dropped into your account, the next month, the interest from the month before gains you a tiny bit more interest, right? So instead of just getting interest on the $1,000, in month 2, you get the interest on the $1,000 plus interest on the interest. So that's what's called compounding. So this is good. So the more often you compound, the more money you get, right? So if you had an option to compound daily, which is sort of not a general option, but if it were, that would be better than monthly, right? The more you do it, the more money you make, okay? So parts A and B are meant to give us an overview of what these two formulas are and what they represent. So now what we want to do is we want to start thinking about the things that we've been doing in terms of rate of change and how that might apply here. Okay, so for part C, for each of these general formulas, right, so the one that's up here and the one that's over here, okay, we want to try to find the rate at which the future value is changing. So what does that mean? We are trying to find the derivatives of these functions. Okay, so in order to do that, we have to remember that our independent variable is t, time, and that present value and rate are constants, right? So that's going to be important when thinking about these types of functions. These are exponential functions because you see the t up in the power. So we want to try to find the derivative of this function and of this function. The first one is definitely easier than the second one, but it's still not easy in general. These are exponential functions, so think about what are your constant multiples, what is the base, and what is the variable. And then for the second one, I need you to think about the algebra that we would need to do so that we have an exponential function, so something raised to the t. We did this earlier at the beginning of class with the algebra on the example e to the cx. We have to apply a similar logic to rewrite this here before we can take the derivative, okay? So I'm going to give you 3 minutes. Think about how you can do this. Your derivative will still have a PV, an R, and a T, all of those things in it, as well as other things that come out. So try this out, take about 3 minutes, and then we'll go through it together. Okay, take about 30 more seconds. Okay, so let's start with future value equals present value, 1 plus r to the t. So when we think about taking the derivative, the things that are going to be important are, do we have a constant multiple? What is the base? What is the power? And so here We do have a constant multiple. This PV is a constant, which means that it's going to multiply the derivative of the function. Now, when we think about the function, we have 1 plus r, which is the base, and we have t, which is the power. So when we take the derivative, we get the same thing back, 1 plus r to the t, times the natural log of the base. Okay, so it should be the natural log of 1 plus r, because 1 plus r is the thing that is raised to the t power. Okay, so now when we change our equation to be compounding monthly, we have future value equals present value, 1 plus r over 12 to the 12 times t. Before we can do that, we have to rewrite it so that we have a base raised to a power. That's how we get an exponential function. So the constant multiple doesn't change, but what we want to do is we want to pull apart the 12 and the t. That's the part that's tripping us up here. So I can do that by separating them as a power to a power. And I want to pull the constant down and leave the t up here so it's an exponential form. And so what that does is it changes what the base is. Okay, so the base is here, the power is now t. So now when I find my derivative, I have PV, that's the constant multiple. I get the same thing back I started with. So 1 plus r over 12 to the 12 times t. You can write it unseparated in this part or separated, doesn't matter. But what really gets impacted here is the natural log of the base. So I have to be really clear about what the base is so that I get this constant right. So my base here is 1 plus r over 12 to the 12th. So that 12th power has to be part of the base. Okay, so now my derivative looks like this. So the final question here is actually calculating something using this derivative. So we want to calculate the rate at which each function is changing. So these two functions, the rate at which they are changing is the derivative. At time equals 3, so in the middle of this 5-year process, when present value is 1,000 and the interest rate is 0.025. So we're plugging in these values very carefully and then coming up with the rate at which it's changing, and then making sure that we include units to pair with our number. Okay, so we are going to plug things in and we are going to round to 2 decimal places since we're talking in a monetary system here. So you're going to find the rate at which we're changing for each of these functions. And remember, annual, monthly compounding, we would expect that the monthly compounding rate will be slightly higher since we end up with more money in the end. So I'm going to give you 2 minutes. I want you to plug in these values into the rate, think about what the units are, and think about what it's telling us in the context of this problem, and then we'll go through it together. Okay, take about 30 more seconds to finish up your calculations. All right, so for our first one, we have to carefully plug into the derivative, present value, 1 plus r to the third, because we're looking in year 3, natural log of 1 plus 0.025. When we plug that into the calculator, we're going to get 26.59. And what does that mean, right? So what are the units? What does that tell us? And so as a reminder, when we talk about the derivative, we take the units of the dependent variable over the units of the independent variable. The dependent variable here was future value, which was in dollars. So we have $26.59. And then the independent units were time t in years. So that means that my investment is growing, because it's positive, at a rate of $26.59 per year when we're in the third year. Okay, that's what that means. Okay, for the second one, there's a lot more sort of calculation places that could go wrong. So try to be extra careful with your parentheses and your powers. I mess these up all the time. So you want to think about your answer and if it makes sense. So when we plug this all in, I get $26.92 when rounded to 2 decimals, and I know that's per year. That makes a lot of sense to me, right? Because I know that this one should be slightly bigger, because I know compounding monthly gets me a little bit more money, but only a little bit more money. So these should be close, but this one should be bigger. So I'm feeling pretty good about my parentheses in this calculation. And again, for the second one, this means that my investment is growing at $26.92 per year when we are at the 3-year mark for compounding monthly in my investment. Okay, so again, we are able to apply our exponential rules here in sort of a different type of way. As long as we recognize it's an exponential function, we can talk about the rate of change and carefully apply those formulas as needed. So on Thursday, we'll be picking up with the chain rule. It'll be really helpful if you have pretty good understanding of the basic rules we've talked about so far. Again, basic is not easy, but the power rule, the exponential rule, sine and cosine, that'll all be really helpful if you're pretty comfortable with those for Thursday. So if you need to work on those on homework or anything before then, please do. And then on Thursday, we will start the chain rule. Have a great rest of your day.